With the birth of algebraic equations always comes the question, which types of equations have solutions and which don't? And in which number systems do those equations have solutions versus other number systems where they may not have solutions? And also, how many solutions are there? Well, today we're going to look at a pretty classic equation and we're going to solve it in 6 different number systems. And so let's start by solving the equation x squared equals -1. Well, over the simplest one, r. Well, of course there's no solution, so let's move on. Okay, so now moving on to our next pretty familiar number system, the complex numbers. You might know that there are 2 solutions, I and -I. And in fact, this is a quadratic equation, and every quadratic equation in complex numbers has 2 solutions up to multiplicity, of course. It could have a repeated solution. And this goes for polynomial equations of degree n. They have exactly n solutions up to multiplicity. So the complex numbers are really nice like that. But that being said, this equation has 2 very simple solutions to find. So that leads us to our next number system, the Hamilton Quaternions. And this is where things start getting interesting. So let's recall what that is. So that's going to be the set of everything of the form a plus bi plus cj plus dk. A, b, c, and d are real numbers, whereas I, j, and k are maybe these other objects that satisfy some pretty interesting multiplicative properties. So they have this property that I squared, j squared, and k squared are all -1. So that looks like 3 copies of the complex numbers, but when you take their product, even more interesting stuff happens. So I times j equals k, whereas j times I is -k, so they are not commutative. Furthermore, j times k is I, where k times j is -I, and k times I is j, whereas I times k is -j. Now, I guess I should maybe point out that there's another relation that often people state, and that is I times j times k is -1. And in fact, these lower 2 equations, or sets of equations really, are all you need. You can take I times j times k equals -1, and then all of their squares equals -1, and produce these equations up here. It's just like a little bit of work to get there. Maybe try it out if you've never done that calculation. Okay, so now we're looking for things that square to -1 here. Well, obviously I squared, j squared, and k squared to -1. And -I, -j, and -k all square to -1 as well. That gives us 6 solutions. But can we find more? Well, let's look for an arbitrary solution like this. So a plus bi plus cj plus dk, and we need to square it. So let's put another copy as well. So a, bi, cj, and dk. And let's multiply this out to see what we get. So there's lots of terms to hit. There are 16 total multiplications to do. So we'll do a times a, that'll give us a squared. We'll do bi times bi, that'll give us -b squared. Likewise, we'll get -c squared and -d squared. Okay, then we'll have a times bi, that'll be plus abi, but we get 2 of those. And we don't have to worry about commutativity here because the commutativity within the real numbers is clear. So we have 2abi. And then similarly, we have a, cj from 2 places. So that'll give us 2ac times j. And finally, 2ad times k. Okay, great. And now what else do we have? Well, we'll get the terms that come from the pure imaginary parts multiplying into each other. I'd like to point out that these things that are combinations of I, j, and k are the pure imaginary parts of the Hamilton Quaternions. So let's see, we'll have bi times cj, so that'll give us plus bc times k, because we have I times j in that order. But then we'll also have cj times bi. but that'll give us negative bc times k, because that gives us j times I in the opposite order. Well, check it out. These two will cancel. And that'll happen with all of the rest of the terms as well. So let's see, bi times dk will be negative bdj. And then let's see, dk times bi will give us plus bdj, because that product is occurring in the opposite order. Okay, and then those will cancel as well, because they have opposite signs. And then finally, we'll have dk times cj, so that'll give us, let's see, k times j from our chart up here is negative I, so it'll be negative cdi, and then we'll have a corresponding plus cdi from the last term. I'll let you find that last term if you don't see it. And now those will cancel as well. Now, let's notice that we want this to be equal to -1. So let's maybe point that here. This is what we want, because we're trying to solve the equation x squared equals -1. Well, all of these terms right here are attached to I, j, and k type terms. So all of the coefficients here have to be equal to 0. But notice all of those have a in common, so it follows that a has to be 0. So let's put that here. So we have a is equal to 0. Okay, but that means that this term will also 0 out. Okay, nice. And now let's bring this down. So if we set x equal to this pure imaginary number, bi times cj times dk, then that tells us that x squared is negative b squared plus c squared plus d squared. Okay, and that's from setting a equal to 0 by our calculation that told us that that was essentially the thing to do. Okay, so now we want this to be equal to -1, so that's our goal. So for this to be equal to -1, we need b squared plus c squared plus d squared to be equal to +1, because we've got this minus sign out here. Okay, but if those square and sum to +1, that's like these things being on the surface of a two-sphere. So if you think about this as having the B, C, and D axes. So how could we get those on the surface of a two-sphere? Well, we want to be motivated by spherical coordinates from calculus maybe 3, a multivariable calculus class. That gives us a way to parameterize the unit sphere pretty easily. So let's take B to play the role of x, like you would usually see in multivariable calculus, C, Y, and D, Z. So that tells us that B should probably be cosine theta times sine phi, and then C should be sine theta times sine phi, and then finally D should probably be cosine phi. And you might say, well, what are the allowable values of theta and phi here? Well, theta will go from 0 to 2 pi, and then phi will go from 0 to pi. And let's just recall that theta was like the angle around maybe the equator, whereas phi was the angle up from the South Pole. That's why you need less values of phi here. Notice that gives us infinitely many solutions because, well, we could take theta and phi to be anything on those intervals. Furthermore, since those are intervals, they're uncountable. So that gives us uncountably many solutions. And now let's just look at a particular example, one that works out pretty nicely. Let's, for example, take the case when theta equals phi equals pi over 4 and see what we get. So in that case, we'll have x equals, well, cosine theta times sine phi. Well, they're both 1 over the square root of 2 here, so they multiply together to give us a half. So we have half I, similarly half j plus 1 over root 2k. So there's an example of a square root of -1 that's maybe a little bit harder to find than simply I, j, and k within the Hamilton Quaternions. Furthermore, this is like a pathway to find infinitely many of them of your choosing. Okay, nice. And now moving on, we'll look at this equation in the space of 2 by 2 matrices. And for the purposes of this video, we'll take our coefficients from R. But you could also take them from C or some other set if you wanted to. Okay, so let's just recall 2 by 2 matrices are of this form. Our entries come from R. Let's set X to an arbitrary 2 by 2 matrix. And now let's square X. So that means we need to multiply A, B, C, D times the matrix A, B, C, D. So let's recall the rules of matrix multiplication. We take this first row and swivel it into the first column. The entries overlap, we multiply those and then add. So that gives us A squared plus BC in this entry. Actually, I made a video on why matrix multiplication is the way it is. Maybe you could check that out at the end of this video. I think it's a good one. Okay, now moving on, we'll have this AB swiveling into this BD. That'll give us AB plus BD. So there we have that there, AB plus BD. And then similarly in this bottom right entry, we have AC plus CD. And then finally, swiveling this around, we have BC plus D squared. So there it is, BC plus D squared. And then recall our goal is for this to be equal to -1. Well, what do we mean by -1 inside of this M2 by 2 R space? Well, I think the logical thing to think here is just negative the identity matrix. So that would be the diagonal matrix with -1s on the diagonal. So check it out. That gives us a system of 4 equations and 4 variables. Perhaps we could solve that. So let's write those equations here. We're really just transposing them over. So we've got A squared plus BC equals -1. Maybe we'll also write this. We have BC plus D squared is -1. We'll keep the -1s together. And then we also have AB plus BD equals 0, and then AC plus CD equals 0. Let's notice that these second two can be factored a bit. This one has a common factor of B, this one has a common factor of C. So here we'll have B, and then A plus D equals 0, and then likewise we'll have C, and A plus D equals 0. And that really means it boils down into a couple of cases. Well, we've got the case when B and C are 0, or we've got the case when A plus D equals 0. So let's look at those separately. So case 1, maybe let's say that's the case when B and C are 0. Notice that we need both of them to be 0 for both of those equations to be 0. I guess we could have B as 0 and A plus D as 0, but that'll be taken care of in the A plus D equals 0 case. Okay, so B equals C equals 0. Okay, but looping that back into the first two equations, that tells us A squared equals D squared equals -1. But since we're working over M2 by 2R, that gives us no solution. Now, of course, you could play the game where we're working over complex numbers, and you would get solutions out of this, but let's just not do that here. Okay, so now let's move on to the second, more fruitful case, which is when the sum of the diagonal entries, or A plus D equals 0. In other words, the trace is 0. So that means we have D equals -A. So now looping that back into previous equations, what do we have? Well, these are the only two remaining equations. And they both give us the same thing. That's because D squared is the same thing as -A squared, which is the same thing as A squared. So we could perhaps solve this equation for C. So that gives us something like this. We have B times C equals -1 minus A squared. And then from there, let's notice that this right-hand side is definitely not 0. Because if this right-hand side were 0, that means A squared would be -1. But if A squared is -1, then we're inside complex numbers, and we can't have that. So since that right-hand side is non-zero, that means the left-hand side is non-zero, which means that B and C are both non-zero. But that's good news. That means we can divide by either of them we would like to. Let's maybe divide by B, and that'll give us an expression for C as -1 minus a squared over B. And then finally, that gives us a form of X, our original matrix up here. And in fact, there are infinitely many such X's. So notice we have A, B. The first row is free. And then in this entry down here, we have -1 minus a squared over B. In this entry down here, we have minus a. And you can check that that squares to negative the identity matrix, although it necessarily does based off of the structure that we've done here. I guess I should say that this is parameterized again by all real numbers. So this is an uncountable number of solutions, just like we had before with Hamilton's quaternions. Is this more solutions? Well, in a sense, it's more solutions because that was parameterized by 2 intervals, whereas this is parameterized by all real numbers. But it's uncountable, so in a sense, it's not more solutions as well. Okay, so anyway, let's look at a special example of this where we set A equal to 3 and B equal to 2, and we can get a nice example of this with integer entries even. So we have 3, 2, and then -5, -3. So there's an example of a matrix that satisfies this equation with integer entries. Okay, so we've done our task for 2 by 2 matrices. And now we're going to move on to solving this in ZP. And you might say, well, what is ZP? Well, it's a field with P elements. Well, what's a field? Well, it's a set where you can do like nice operations like addition and multiplication, and all of the rules that you would like to exist, like associativity, commutativity. We have inverses for everything with addition and almost everything except for 0th multiplication. In this case, you can take the elements to be 0, 1, 2, up to P-1, and then you do operations of addition and multiplication as normal. You just reduce mod P at the end. You divide by P and keep the remainder. So solving this equation in ZP is equivalent to solving the congruence. X squared is congruent to -1 mod P. And we're going to prove a theorem that will tell us when this has a solution. And then I'll just tell you that if there is a solution, there are exactly 2 solutions, but we won't prove that. And so this has a solution if and only if P is congruent to 1 mod 4. In other words, it's a prime that's of the form 4n plus 1. I guess I forgot to say that P has to be a prime number here. Okay, so this is an if and only if statement, which means there are 2 directions to prove. Let's prove this forward direction first. Okay, so let's suppose that x squared is congruent to -1 modulo P. Okay, and then let's raise that whole equation to the power P-1 over 2. Now notice, because P is congruent to 4n plus 1, P-1 over 2 is, well, it's a natural number, so we're okay there. And then at the same time, I'm going to flip this. So we have -1 to the P-1 over 2 is congruent to x squared to the P-1 over 2, but that turns into x to the P-1. Oh, but by Fermat's little theorem, that is congruent to 1 modulo P. Okay, but now we've got -1 to some power is congruent to 1 mod P. But working mod P is like very predictable. It acts a lot like the integers. And you might say, well, when do I raise -1 to some power and get 1? Well, it's when that power is an even number. So that's our takeaway here. We have P-1 over 2 is even. I can write it as 2n. Okay, but now I can just multiply both sides by 2, and that gives me P-1 is equal to 4n, which tells me that P is equal to 4n plus 1. Oh, but that means that P is congruent to 1 modulo 4 as needed. Okay, so that's this forward direction. Now let's do the reverse direction. So for our reverse direction, let's use something called Wilson's theorem, which says that p minus 1 factorial is negative 1 mod p when p is a prime. And the idea here will actually construct a solution. So let's take this p minus 1 factorial and write it out. So that'll be 1 times 2 times 3 times 4, ending at p minus 1. But I'm going to stop in the middle for a little bit and write this as p minus 1 over 2, and then p plus 1 over 2, and then on and on and on until we get to like p minus 2 and then p minus 1. So we know that is congruent to negative 1 modulo p, like that. And now I'm going to do a little bit of grouping. So I'm going to group these and these. So I know that those are exactly halfway grouped because p minus 1 is even because p is odd. I guess I should have said that p is an odd prime here, but I think that's okay. And then we can replace everything out on this right-hand term with its negative. So let's do that. So let's just bring this first term down. We have 1 times 2 times 3, ending at p minus 1 over 2. And then this p plus 1 over 2 is actually the same thing as negative p minus 1 over 2. And then that's going to end down here at p minus 2, which is the same thing as negative 2, and p minus 1, which is the same thing as negative 1. Oh, but that's also congruent to negative 1 modulo p. But now we can factor a bunch of minus 1s out. How many minus 1s can we factor? P minus 1 over 2 of them. And then we've got these two products which are exactly the same after factoring the minus 1 out. So that leaves us with what is actually p minus 1 over 2 factorial after, like I said, those primes are factored out. And then we have this is p minus 1 over 2 factorial all squared after those minus 1s are factored out and those two are smashed together. And this is congruent to negative 1 modulo p. Still, I haven't changed the right-hand side of this congruence. Oh, but we haven't used the fact that p is congruent to 1 mod 4 yet. But since p is congruent to 1 mod 4, we know p minus 1 over 2 is even, but that means this is negative 1 to an even number, so this just turns into positive 1, so we can almost just forget about it. Oh, but now we have something that squares to negative 1, so that's our solution. This p minus 1 over 2 factorial is our solution. And in fact, we'll have two solutions. P minus 1 over 2 factorial and negative p minus 1 over 2 factorial will be our two solutions to this congruence. Okay, so that's this sorted for ZP. Okay, so now let's briefly sketch out what might be happening in Zn, where n is composite. And we'll do this with the example Z65. And you might say, well, why 65? It's because 65 is equal to 5 times 13, and those are the smallest two primes congruent to 1 mod 4. And thus we have solutions in their setups. Okay, so we want to solve the following equation. So x squared congruent to negative 1 modulo 65. Okay, but one path to solving this would be to split it up into two pieces. So we could split this up into the piece x squared congruent to negative 1 modulo 5 and x squared congruent to negative 1 modulo 13. And in fact, we could find solutions for each of those. You can very quickly find the solution for x squared congruent to negative 1 mod 5 because 2 squared is 4 and 4 is negative 1. And what's another one? Well, 3 is also a solution. Well, that's actually negative 2, right? And that's because 3 squared is 9, which is 1 less than 10. And then we can maybe just guess and check for solutions mod 13 as well. Notice that x equals 5 is the solution because 5 squared is 25, but 25 is 1 less than 26. But then 13 minus 5, in other words, negative 5, which is 8, is also a solution. Okay, and then from there, we could spread these out to like infinitely many solutions over integers. So they're not unique mod 5 or 13 anymore, but they do spread out. So here we would have like x equals 2 plus 5k as k goes through all of the integers, or x equals 3 plus 5k as k goes through all of the integers. And down here, we would have x equals 5 plus 13, let's say m, as m goes through all of the integers, and then x equals 8 plus 13m as m goes through all of the integers. And really, you only have to look up to 64. That's because we're working mod 65 here. And then you would just look at all of those sets of numbers that follow into those different possibilities. Perhaps you would choose x of the form 3 plus 5k, and then x of the form 8 plus 13k. Maybe that would be your choice. Or you could choose 8 plus 13m and 2 plus 5k. That could be your choice as well. And then you compare all those until you find your solutions. And in this case, I'll just tell you that you'll get solutions 8, 18, 47, and 57. Now, 8 and 57 are related because 57 is negative 8, and 18 and 47 are related because 47 is negative 18. Now, let's just really quickly check that this works. Notice that 8 squared is 64, but that's 1 less than 65, so we're good to go there. Okay. So we didn't go far into what's happening in Zn, but the number of solutions could be 0 or more. Actually, if n is composite and maybe like, and with more structure than we saw, well, a lot of different things could be going on. Okay, so that wraps up all of the cases I wanted to look at. So do you have any other interesting ideas of places where you could solve x squared equals negative 1 and find other types of solutions? And that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.